It's my pleasure to introduce Professor Vjacheslav Yurko. I hope my pronunciation was not so bad, who is, well, also a co-organizer from Saratov State University, and he will talk about method of spectral mappings in the inverse problem theory. So please start, Professor Yurko.
Oh, thank you very much. First of all, I want to say that our conference is very interesting and useful, and the most contribution in the organization of this conference is made by Ricardo. So, Ricardo, we have to say to you thank you very much for your activity in this direction.
Well, you're most welcome.
So, the title of my talk is the method of spectral mappings in the inverse problem theory. We will pay attention only to one class of inverse problems, namely inverse spectral problems for ordinary differential operators. And we will consider the method of spectral mappings, which is the effective and universal tool for studying this class of inverse problems. So first I need some historical remarks, very, very short, not review, only short remarks which are necessary to understand what's going on. So we start with the simplest object in the theory, namely Sturm-Liouville operators on a finite interval. This object is the simplest one, and on the other hand, is the first from the historical point of view. So we need some notations. We consider the boundary value problem L for equation 1, Sturm-Liouville equation. Lambda is the spectral parameter. And for definiteness, we consider the Robin type boundary conditions. Of course, it's possible to consider other boundary conditions. Let phi and s be the solutions of equation 1 under the initial conditions, the following one. And we introduce the function delta. By definition, it's v of phi. This function, the statements. You see, it's known that the specification of one spectrum, only lambda n, it's not sufficient to reconstruct the potential Q, not sufficient to solve the inverse problem. And we need to add something. And Marchenko suggested to add the weight numbers. All together, lambda n together with alpha n usually are called the spectral data. So inverse problem 1, given the spectral data, construct the potential Q at the coefficients. The Sweden mathematician Borg suggested another statement. He suggested to add the second spectrum. For example, we can take the boundary value problem L1 for the same equation, but with a little bit different boundary conditions. And this inverse problem 2, given two spectra, lambda n and nu n, construct the potential Q and the coefficients. These statements are good enough in the following point of view. The specification of the spectral data, lambda n and alpha n, uniquely determines the potential. So these data are sufficient for studying inverse problems. And similar with Borg's statement. The specification of two spectra is sufficient for studying inverse problem. In this case, in this sense, these statements are correct. But on the other hand, these statements are not natural. And in this sense, it's not good. We need another statement, more adequate from mathematical point of view and from physical point of view too. Unfortunately, such a statement really exists. Let's consider the following notations, notions. Let phi capital be the solution of our equation under the boundary conditions, not initial, it's boundary conditions. And we introduce the function m of lambda. By definition, it's phi at 0. And it's natural to call the solution phi the wild-type solution and the function m the wild-type function, because the classical wild function is defined a little bit different way. But for simplicity, we omit the word type, and I call this function the wild function. So inverse problem 3, given the wild function m of lambda, construct the potential Q and the coefficients. This inverse problem, of course, is equivalent to inverse problem 1 and inverse problem 2 because of formulas 2 and 3. For example, if we have spectral data lambda n and alpha n, we can reconstruct the wild function m by the formula 2. And on the contrary, if we have the wild function m, we can calculate poles and residues and find the spectral data. And similar to inverse problem 2. So these three inverse problems are equivalent each to other. But inverse problem 3 is the most natural from many points of view, from mathematical and from physical. For example, in many physical applications, namely the wild function can be measured. As example, I can mention the paper.
Could you remind the definition of little delta lambda, please?
Delta lambda is the characteristic function of the first boundary value problem.
Could you remind the definition, please? Like on the slide.
Okay. This one. Delta is v of phi. It's the entire function, zeros of this function coincide with the spectrum.
Thank you.
So the specification of the spectrum is equivalent to the specification of the characteristic function. You see, I mentioned the paper by Andrei Tikhon, where he studied a geophysical problem, and in this problem, we can measure just the while function. And you see, from many points of view, I have no time to discuss this problem in details, but nevertheless, this statement is the most natural. And moreover, it's very natural for different generalizations, because sometimes it's natural to construct the generalized similar object like while function for other classes of operators. So, and the similar situation of the half-line. We can introduce the while type solution, and we have here the condition at infinity. This exponential is vanishing. So roughly speaking, this means that phi at infinity is 0. And the definition of the while function is the same. So how to solve these inverse problems? Since this inverse problem is nonlinear, there exist some local approaches. For example, Borg's approach is local. So we can study such a problem locally. But of course, we need the global method, global approach. Global means we would like to solve this nonlinear problem globally. And this method was created by Soviet mathematicians Marchenko and Levitan. And it's possible to explain how it works in 2 minutes. You see, first, this method usually is called the transformation operator method. Sometimes it's called the Gelfand-Levitan-Marchenko method. But the contribution, Gelfand's contribution is very small. So really the authors are Marchenko and Levitan. And I prefer to call this method the wave method, because the main equation, which will be the next slide, is a particular case of the Riemann formula for the solution of Cauchy problem for the wave equation. So the following representation is valid, 6. It's important that the kernel G doesn't depend on the spectral parameter. And here is the really transformation operator. If we have the kernel G, then we can calculate the potential and the coefficients by 7. But how it works? Consider the case of a finite interval. We take a model boundary value problem L tilde with 0 coefficients. Of course, it's possible to take arbitrary model problem, and in some applications, it's really better to choose the concrete model problem. But for us, it doesn't matter, and we take the simplest case with 0 coefficients. In this case, the eigenvalues are n pure n square, and we can construct the function f, or using spectral data, or using the y function, where gamma is the contour connected with the behavior of the spectrum. So this function is known from our point of view, and the main result is the following theorem. For each fixed x is a parameter, the kernel G satisfies the linear integral equation. This equation usually is called the Gelfand-Levitan equation. In a little bit different form, sometimes such equations are called Gelfand-Levitan-Marchenko equations, but it doesn't matter. And I already told that this equation is a particular case of the Riemann formula for the solution of the Cauchy problem for the wave equation, one-dimensional wave equation. So important that we can reduce our nonlinear inverse problem to the solution of linear equation. It's the main contribution. It's the most famous result. And you see, this is a Fredholm time equation because x is a parameter. But it's possible to prove the unique solvability of this equation. So we have the algorithm. If we can solve this equation, we get the kernel G and then calculate the potential. So it's clear. And similar situation of the half-life. Theorem 2 remains true for the half-life 2, a little bit different definition of the function f. And this is a very famous method. For example, Marshall and Levitan separately got Lenin prizes for these investigations. And Lenin prizes was the highest prizes in the Soviet Union. Of course, it's natural that just after appearance of this method, a number of mathematicians, including some outstanding mathematicians, they try to generalize this approach, to use this method for studying inverse problems for other classes of differential operators. And from the historical point of view, the first such class was the so-called higher order differential operators. Higher order means order more than 2. The specialists in spectral theory know that there is big difference between second order and third order equations, but no difference between third, fourth, fifth, 1000 order equations. So it's the reason why all equations of order more than 2 usually are called the higher order equations. And studying higher order equations for studying studying the higher order equations, both in direct problems and inverse problems, always much more difficult as the Sturm-Liouville equation. From the point of view of higher order equations, Sturm-Liouville equations are almost trivial. This attempts to generalize this approach for higher order equations, unfortunately, wasn't successful. This method, the transformation operator method, does not work for higher order equations. And moreover, it was found out that this approach, this method works, roughly speaking, only for Sturm-Liouville operators and close to them, like Dirac system and similar objects, close by ideas. And for other classes and for higher order equations in particular, it doesn't work. So we need another method, global method. And this method was created step by step. And I call this method the method of spectral mappings. And here are some references. And I try to compare 2 monographs, 3 and 4. Monograph 3 with my German colleague Gerhard Freiling. In these monographs, we consider only one object, simplest one, Sturm-Liouville operators. And we try to show how these inverse problems can be solved by different methods. So roughly speaking, here we have one object and several methods. And in monograph on the contrary, we have one method, only method of spectral mappings, and several objects. How to use this method for studying different classes of inverse problems. And I've already told that from the historical point of view, the first object after Sturm-Liouville is the equation 11, high order equation class of differential equations of the form 11. And the method of spectral mappings was created just for this object, for the concrete object. And only after this problem was solved, it was found out that this method rather universal, can be used for other classes of equations. And so now I try to explain you how it works. And since the technique for 11 is more or less complicated, I suggest the following. My explanation consists of 3 parts. First, I try to explain main ideas very shortly and without formulas, only by words. Then I show how these ideas works in the simplest example, namely for Sturm-Liouville operators. And the third step, we consider just the equation 11, and I try to as simple as possible to explain how this works in the for lab. So first explanation by words. In this method, for different classes of equations, we always start with Cauchy's integral formula. It's our starting point, Cauchy's integral formula. But I'd like to say that our goal in this method looks similar to the transformation operator method. Like in the transformation operator method, we would like to reduce our inverse problem to the solution of linear equation in the corresponding Banach space. The choice of the Banach space, it depends on the class of operators, but our goals is similar. We would like to reduce nonlinear problem to the solution of linear equation. And we start with the Cauchy's integral formula. This formula is already linear. It's very important, but unfortunately, it's not equation. So we have to derive the equation starting from the Cauchy's integral formula. In Cauchy's integral formula, we need to choose the contour and the corresponding functions. And this choice, it's some kind of art. It depends on the class of operators. And usually the contour, the choice of the contour connects with the behavior of the spectrum. And then you see, in the Cauchy's integral formula, we have two variables. One variable lies in the contour, and the second one outside. And roughly speaking, we need to move this second variable to the contour. Of course, it depends on the class of the operator. There are some difficulties in the technique, and the most technical work just in this step. And this technique is quite different for different classes of operators, but the main steps, starting from Cauchy's integral formula, try to get to the equation to derive the linear equation. It's one of the same idea for all classes of operators. So how it works for the Sturm-Liouville operator? The Sturm-Liouville operator is the simplest object, and in this case, the situation is almost trivial. You see how it works. Consider, for example, for definiteness, the case of the half-line. We again choose a model boundary value problem L tilde with zero coefficients. In this case, phi tilde is pure cosine. And we can construct the function A tilde. It's known function because it's constructed from the while function. It's known. And the main results here is the theorem 3. The following relation holds. This relation, you see, it's really linear equation. It's again integral equation, and it's again Fredholm-time equation. It's again x is a parameter, and this equation with respect to phi. And it's possible to prove the unique solvability of this equation. So we again have an algorithm, and the main step of this algorithm is the solution of the equation. This equation, usually such equations in different classes of operators are called the main equation for the inverse problem. So it's main equation. And the algorithm, the main step of the algorithm is we need to solve this main equation. That's all. And the proof of this theorem is so simple that I can show, of course, without details, but very, very shortly. You see, I forgot to say that we can calculate the potential Q using theorem 5. And this formula is better than in the transformation operator method because we have no the numerical differentiation. And I want to say one remark. Now we have many papers devoted to numerical aspects of inverse problem theory, numerical solutions of inverse different type of inverse problems. And you see our experience show that the mesospectral mappings works from numerical point of view better than the transformation operator method. So it's more natural to study numerical aspects of the theory using the mesospectral mappings. Of course, not always, because there are a lot of different approaches. No, but our experience shows that it's better. And even there is a review paper devoted to numerical aspects by the mesospectral mappings. So, in similar situation, it was the case of the half line, but similar situation the case of the finite interval. I promised to say some words about the proof. You see, we introduced some function P11 and P12 using our solutions, and then here is the choice of the contour connected with the behavior of the spectrum, and then we start with Cauchy's integral formula for the contours, this contour, and for these functions. And then very simple technique, almost trivial. It's only one slide, this one, and at the end we have our main equation. So here is almost trivial because the object is simple. The Sturm-Liouville equation is simple enough. But now how it works for higher order equations. Consider our equation 1, and we need some notations. Of course, I try to explain ideas by words, and I will use formulas as less as possible, but nevertheless, we need some formulas, some notations. So we introduce the sectors as new. It's the standard, and many investigations in spectral theory for higher order equations, direct and inverse problems. It's the standard. We divide the row plane into the sectors with the following property. And then our problem is the following. Till now, we have known the statement of the problem. First of all, we need to understand how to formulate the inverse problem. And you see, it's natural to try to generalize the notions of the while function and the while solutions. And it's possible. You see, we introduce the fundamental system of solutions, phi capital M, solutions of our equation with the boundary conditions. You see, if M is fixed, then we have M conditions at 0. Delta is the Kronecker symbol. So M conditions at 0 and one condition at infinity. But this one condition is equivalent to N minus M conditions because we exclude N minus M exponentials. So that's correct definition, and it's possible to prove that such solutions exist and have good properties, unique and so on. And then we can introduce the generalization of the notion of the while function by the following way. We introduce the matrix M. You see the elements M, Mk we measure the function f and derivatives at 0. And I call this matrix the while matrix. First, I call this matrix while type matrix, then I mean the word type. And now in some words, this matrix is called while Yurko matrix. And I try to show you this definition using this example. You see, let n is equal to 4. And then the fundamental system phi m is defined by these conditions. And the while matrix M is a triangular matrix. And the statement of the inverse problem is the following. Given the Weil matrix, construct the coefficients of differential equations. So before studying inverse problems, we need to find properties of the Weil matrix. So first we need to find properties of the Weil matrix, and this means that we need to study direct problems. And these properties consist of three parts: asymptotical properties, analytical properties, and the so-called structural properties. When I started to study this problem, I did not guess that structural properties exist. But it was clear that it's necessary to find analytic properties and asymptotical properties. And it's the easiest part of the work. Of course, there is some technique, but it's no problem. And so it's easy to find analytical and asymptotical properties. And since I did not guess that I need other properties, structural properties, so of course I failed to derive the main equation. And then step by step, it was found out that such properties exist, and they were found. And what does it mean, structural properties? You see, in order to solve the inverse problem, we need the whole matrix. It's not possible to exclude one element. There are counterexamples. So we need to specify the whole matrix. But you see, these elements are not independent. There are connections between these elements. It's nature. It's natural because from physical point of view, these elements are reaction of the object on the perturbation. But object one of the same. So it's natural to wait that there are connections between such elements. And these connections are called the structural properties. And you see, of course, there are concrete concrete theorems, but I think it doesn't matter to speak in details. It's enough to explain it only by words. So we get asymptotical properties, analytical properties, and structural properties. And it's sufficient to derive the main equation. You see, here is theorem of one, but we omit it. You see, it's theorem of one, we have analytic, asymptotical, and structural properties. So, and then after some technique using these properties, we can get the main equation. Really, the main result is the theorem 2. For each fixed x is parameter, the vector function phi is the special solutions of our equation. You see, this vector phi satisfies the linear single integral equation, which is called the main equation. This equation is linear, but with singularity, Cauchy type singularity. So it's essentially more difficult than for Sturm-Liouville operator. And fortunately, it's possible to prove the unique solvability of this equation in the corresponding Banach space. By the way, this equation with respect to phi, the function q and h are known, and they are constructed from the model boundary, the model operator, and from the given the Weil matrix. Of course, we again have an algorithm. The main step of this algorithm is the solution of the main equation. So we again reduce our nonlinear inverse problem to the solution of linear equation. And if we solve this equation, then we have a vector function phi, and using this function, a vector function, we can construct the potentials, the coefficients of the differential equation, just for using concrete formulas. Here, the theorem is the unique solvability in the corresponding Banach space. Of course, it's possible to take another. It's not unique possibility, but it's not the problem and the algorithm. And you see, so this inverse problem is solved. But usually when we studied inverse problems, now we have uniqueness, we have algorithm, but there is another important problem to find the necessary and sufficient conditions for the solvability of the inverse problem. Usually for different classes of operators, this problem is the most difficult part of the investigation. And for this class of inverse problem, for high order equations, this problem was solved and necessary and sufficient conditions was found. But in the slide, I omit them. So I repeat that these results, it was the first results obtained by the method of spectral methods. So this method was created just for solving this concrete inverse problem. But then it was found out that this method can be used for other classes of equations. Now there are many classes of these equations which were solved by this method. And I show you only two such classes very shortly, namely systems of equations and equations on graphs. But I repeat that there are results related to many classes. But it seems to me that these two classes are the most interesting. So inverse problems for systems. Consider this concrete system 1. It's natural to call the system canonical, the canonical system. And you see here rho is the spectral parameter. The potential matrix Q of X we have to construct to find this matrix. But the constant matrix Q0 is known a priori. And you see it's not really restriction, not serious restriction. We suppose that it's diagonal matrix. It's not important. And here I want to emphasize that there are two different cases here. When characteristic numbers qk are real, all are real. In this case, the inverse problem for this system becomes trivial, because it's really simple generalizations of the Dirac system. But Dirac system was solved by the transformation operator method many years ago. And if we consider this more general system with real coefficients, qk, in this case, no difficulties. It's immediately repeat all arguments, and so this inverse problems becomes trivial. But if qk are arbitrary complex numbers, in this case, the situation is seriously more difficult, and even more difficult than for higher order equations. But it's possible to solve the inverse problem similar to the previous one, similar to the higher order equations. Technique is more difficult. This object is more difficult. In technique, especially in structural properties here are more difficult. But the scheme, the steps of the solution are completely the same. And so I show you very, very shortly. You see, again, we divide the sectors. We already introduced sectors a little bit different way. And we consider the matrix H. Oh, by the way, we consider only the case of the half line for definiteness. So we consider the matrix H for boundary conditions. And we introduce the generalization of the while solutions. Again, here phi m is the matrix, and conditions, boundary conditions are here. Delta is the Kronecker symbol, and again one condition at infinity, similar situation, And similarly, we introduce the while matrix and the statement of the inverse problem as follows: given the while matrix, construct the potential and the coefficients. And here's the uniqueness result. And then again, we study properties of the while matrix, and you see, we don't need this technique. It's very complicated. And here's some technique how to formulate these properties. Here you see, here's the structural properties, and it doesn't make sense to explain these technical details. But nevertheless, we can get them. And then we can again introduce a special solution phi of this equation. And with respect to phi, we can derive the main equation in theorem 3, the main theorem here. And here again, the equation with the singularities, because the kernel R has a Cauchy type singularities, like in the higher order equation. And again, it's possible to prove the unique solvability of this equation. Here, technique is more complicated, but ideas more or less similar. And so we get the algorithm. The main step of this algorithm is the solution of the main equation. And it's possible to prove the necessary, to find the necessary and sufficient conditions, theorem 4. Of course, it's I have no time to explain here details, but for us it doesn't matter. And now let's consider the last object, namely, let's consider the Sturm-Liouville operators on graphs. You see, now the spectral theory on graphs, very popular topic, a lot of papers, direct and inverse problems. And of course, we confine ourselves only the approach how to use the method of spectral mappings for the solution of this class of inverse problems. And now the method of spectral mappings is used for other classes of equations on graphs. But in order to explain ideas, I consider only the simplest example. Namely, we consider only Sturm-Liouville operators, simplest object, and the simplest graphs, namely trees, graphs without cycles. And I try to explain, to show you ideas using this simplest object, but in the end of the talk, I say some words about different classes of operators. Moreover, in order to explain ideas only by words, I consider the concrete example. We consider the concrete tree, this one, and how the method works. First of all, about the statement of the problem. It's possible to introduce the notion, to generalize the notion of the while function on this object. Namely, we can consider each concrete boundary vertex, for example, V1. And for this boundary vertex, we can introduce the while function related, namely, to this object. And then we introduce the functions, the while functions for other boundary vertices. So we have M1, M2, M3, M4, M5, and M0. 6 while functions, because we have 6 boundary vertices. And the statement is the following. Given these while functions for each boundary vertex except the root. So not 6, but only 5. So we have 5 while functions for V1, V2, V3, V4, and V5, but not for the root. So given the 5 while functions, construct the potential on 9 vertices. How it works? You see, the method of spectral mappings, we use here the method of spectral mappings, but it's not enough. We need additional ideas. First of all, how we start our investigation. Consider, for example, the HE2 and consider the auxiliary inverse problem. Auxiliary means the following inverse problems. Given only one while function, namely for V2, the function M2, and we can construct the potential only on one edge, only on E2, in the auxiliary problem. And to solve this inverse problem, auxiliary inverse problem, we can use the method of spectral mappings. I was asked several times by different specialists why it works. It really looks strange because the while function M2 have information from the whole graph, not from one edge. So it's global information, but we solve this problem only local. So it's a little bit strange. I have, of course, explanations, but I am not sure that my explanation is good enough, and that I have no time to discuss it. So nevertheless, we can solve the auxiliary inverse problem by using the inverse, by using the method of spectral mappings. So what else? Suppose we already construct the potential Q on E2, and then we repeat our calculations, and using the while function M3, we can construct the potential on the HE3. What else? Now we would like to go inside the tree. For example, we'd like to reconstruct the potential on the HE9. For this, we cut two edges, E2 and N3. By the way, this idea I call the pseudo-cut in the tree. And we cut E2 and N3, but only for a while. Only for a while. We cut and consider the subtree. In this subtree, V9 is the boundary edge. But we know the while function related to this boundary, this vertex. And the technical problem is how to calculate the while function for V9 using the previous information. And it's possible. There are concrete formulas. So we cut these trees. Then we use the concrete formulas and can calculate the function, the while function M9 related to V9. And then we can again repeat our calculations, use the method of spectral mappings, and construct the potential on E9, and so on. But here's an important remark. Suppose we really construct the potential on E2 and N3 and E9. And now we go on to the E4 and E5. If we start our procedure here for sub3, we failed. It's not possible to get the solution. First, we need to reconstruct the tree. We cut these two edges only for a while. Now we reconstruct them and consider the whole tree again. And then we can start our procedure for E4, E5, then for E8, and so on and so on. And then we can go inside till the root. So, roughly speaking, the ideas here consist of two parts. We can solve auxiliary inverse problems for each edge by method of spectral mappings, and we have the pseudo-cutting procedure. These two main ideas altogether give us a possibility to solve the inverse problem. So then we omit several slides because in the slides is the realization of these ideas. Some we omit them. Here is the cutting, explanation how to cut. So we omit them. And the last slide of my talk, you see this ideas, this approach can be used not only for trees and not only for Sturm-Liouville operators, but many classes of inverse problems on graphs, namely Sturm-Liouville operators on arbitrary compact graphs. This means that we can study cycles, graphs with cycles. Then we can study Sturm-Liouville operators on non-compact graphs. And by the way, these classes we already solved, so it's already known results. Then we can consider not only Sturm-Liouville operators, but higher order differential operators on graphs. Then we can study more complicated case, variable order differential operators. Variable means that we have equations of different orders on different edges. It's very popular boundary value problems in some applications. For example, sometimes in some edges we have second order equations, and at some edges fourth order equations. It's a very popular situation. So variable order is actual class. Then pencils of differential operators we studied. Pencils means differential operator depends on the spectral parameter non-linearly. Non-linear dependence on the spectral parameter. The last class differential operators with singularities or different type of singularities. So of course, it's not all. It's only main classes. Only main classes, and now there are 100 works related to these classes of operator and other classes. So this approach is more or less effective. And you see, it's not my goal to give a review. Of course, there are other results by other approaches. By the way, I forgot to say that this approach was used for studying the concrete inverse problems. Namely, we consider the case when the graph is known, the structure of graph is fixed and known. And we would like to reconstruct only coefficients on the coefficients of the differential equations on graph, not the structure of graphs. Graph is known. Now, of course, it's the most important and most difficult class of the inverse problems. But of course, there are other classes of inverse problems. There are many papers devoted, for example, to the problem when we have, for example, simplest equation without potentials, like pure Laplace one-dimensional, and but we don't know the structure of graph. And using some spectral characteristic, we would like to describe the structure of graph. It's different kind of problems. Of course, it's only a part of the investigations. There are other investigations, and there is a review paper, my paper from 2016 in the Journal of Russian Mathematical Service. But even in this big paper, only a part of the problems were considered, since it's a very huge area. It's not even in big review paper, it's not possible to mention all. But in my talk, of course, I mention only this part of work. And the very last remark, historical remark. I repeat that it's not my goal to have a review, but one remark I want to say. You see, at the beginning of my talk, we saw that the transformation operator method works only for Sturm-Liouville operators. But what about graphs? Is it possible to use this approach, the transformation operator method, to study inverse problems for graphs? It's possible, but only for simplest object, namely Sturm-Liouville operator and the simplest class of graphs, namely graphs without cycles, only trees. And there is a paper by Belishev. Belishev is a Russian mathematician, and he studied this class, Sturm-Liouville operators on trees, using the transformation operator method. Not pure version, but some modification. Some modification of the transformation operator method. He calls this modification the boundary control method, but really it's not separate method. It's a modification of the transformation operator method. And using this method, it's possible to prove the uniqueness result. But unfortunately, in order to use the transformation method approach, we need to specify more spectral data than it's necessary. Additional spectral data we need. In other words, this inverse problem is overdetermined. Otherwise, it doesn't work. So even for this simplest object, the method of spectral mappings with the pseudo-Kaizen procedure works more effective. And you see, maybe seems to me that it's enough. So that's all. Thank you for your attention.
Thank you for this very nice talk. Well, questions. There was a question by Vasilis. Vasilis, are you there?
Yeah, can you hear me?
Yes.
Yes. Yes.
Yeah, it was a very interesting talk, I think, and quite a few questions. But maybe the first question is, in the operators, do you have to assume that the coefficients are real, or you don't even need that?
Sorry, one more.
If you assume that the coefficients are real in your operators.
But you see, it's not necessary to require that the coefficients are real. It's possible to, you see, usually sometimes, you see, in the direct problems, it makes sense to study self-adjoint operators separately. The class of self-adjoint operators are important. This class is important, and it's natural to study this class separately. But in the inverse problem theory, the self-adjointness, it's not important. Not important. And it doesn't matter to consider non-self-adjoint and self-adjoint. Of course, for non-self-adjoint, sometimes we need additional conditions, but the method works for non-self-adjoint similar way like the self-adjoint. So if the coefficients are real, it's not important.
Okay. That's also very interesting because it's more an analytic method, I think. I guess you're familiar with Levinson's solution of the inverse problem, which uses Cauchy integral formula, basically.
You mean Levinson's paper of 1949?
49, something, yes.
By the way, it's very interesting question, very important question. Yes, it's this paper is very interesting. But you see, in the paper of Levinson's paper, there are no results. It's methodical paper. He repeat results of Borg's and Martian. No, Martian a little bit later. Borg's result. No new results. But his approach is very interesting. He used the counter-integral method to prove the uniqueness results. He can prove only uniqueness results. But he was the first who shows that it's possible to use the counter-integration technique in the inverse problem theory. For me personally, it was very important. When I was a young mathematician, I found this paper. And after this paper, I thought that, oh, it would be good to use the counter-integration technique. And you see, in the method of spectral mappings, really, the counter-integration technique is used. So in this sense, Levinson's paper is very important. But no results. It's only methodical one.
Yeah, I thought the philosophy reminded a little bit what you were doing, the philosophy of Levinson's idea. But and I have one more question. In your Weil matrix, you have a lot of entries, a lot of elements. It looks like as you said, there are relations between the elements of the Weil matrix, because otherwise seems to be overdetermined. The information you have, the spectral information.
No, it's not overdetermined. By the way, it was a question for discussions. And you see, there are connections between them, but it's not possible to exclude one of the elements. All elements are needed. And it's not overdetermined. You see, only for Sturm-Liouville equation, only for simplest object, there are no structural properties, and spectral data are independent. But for more complicated situations, it's always have connections between spectral data. It's natural. I already told in the physical applications, it's suppose you have some box, black box, and do you want to study the inside structure? But how to do it? We can knock at this box, some perturbations, and then obtain the reaction of the box. The Weil function, each element of the Weil matrix is a concrete reaction. And you see, one reaction is not enough. It's not sufficient for solving problem. We need one more reaction, and one more, and one more, many reactions. But you see, object one of the same. So it's natural that there are connections between these reactions. It's reactions one of the same object. So it's not overdetermined. But there are connections. It's natural. It's only for Sturm-Liouville, only for simplest situations there are no such connections. But mostly, in all situations, there are connections. It's not overdetermined.
Okay, thank you. Thank you.
Is there any other question?
Yes, may I, Ricardo, please?
Sure.
Vyacheslav Anatolyevich, many thanks for your very interesting talk. You mentioned a review paper on numerical aspects of spectral mapping method. Do you mean the paper with Ignatiev, or there is?
Yes, with Ignatiev. But you see, this review paper, of course, is not complete one, because we studied, you see, Ignatiev is very good specialist in numerical analysis. And he and his students have many experiments, but unfortunately they published not good enough. Many such experience without publications. But we try to understand how the method of spectral mappings works in the numerical aspects, and in many situations it works better than the transformation operator method. But of course, I'm not sure that it's always. Of course, the situation is rather rich and rather many different situations, and I'm sure that sometimes the transformation operator method works better. But mostly, in our experience, mostly the method of spectral mappings works better.
Okay, thank you.
Any other question? Well, I have a question. You mentioned that you obtain also necessary and sufficient conditions, so characterization. Could you somehow describe what is involved in these necessary and sufficient conditions?
Okay. You see, in the slides there are concrete formulas, but it's better to explain by words. You see, we need to find the conditions under which you see, for example, Weil matrix. We take arbitrary matrix, and we need to find the conditions under which this matrix will correspond to the concrete differential operator. And of course, by necessity, we found analytic, asymptotic, and structural properties. And of course, there we have to include these properties in sufficient conditions, because by necessity, we have these conditions. So the first part of in necessary conditions sufficient is the analytical, asymptotical, and structural properties of the Weil matrix. It's the first group of the conditions. The second condition, the important condition, is the solvability of the main equation. By necessity, we prove this. By necessity, it's possible to prove that this linear equation is uniquely solvable. But in sufficiently part, we need to require this. It's the same in the Sturm-Liouville equation. For example, in Marchenko works, it's the same. We need only for self-adjoint case, we can prove the unique solvability of the main equation even for sufficiently. In this case, for self-adjoint case, we don't need this condition. But in non-self-adjoint case, we need to include this condition. And the last condition is you see, we construct the coefficients, and we need to require that these coefficients belongs to the concrete class. For example, they must be integrable. So one more, three groups: properties of the Weil matrix, solvability of the main equation, and the constructed coefficients must belong to the concrete class.
Well, thank you. And then we thank Professor Yurko for this very interesting and illuminating talk.
Thank you very much.
Okay.
So I try to
You should unshare.
Control L, yes?
Escape. No, escape. Use an escape.